Good afternoon. I'm very happy to be here. Thanks for the opportunity to be able to present you some of the work we're doing in Australia. I'm Adrien. I work for the Australian Bureau of Meteorology. I was seconded to the University of Queensland. That's why you have the Uni of Queensland here. And I work with a number of people as part of that work. We got money from google.org over 3 years to do some work with weather radars and fire. That project is still going on. We have a PhD student who just started, but it's only the PhD student, so it's really phasing out. And there are a number of students as well who worked with me here. Catherine, oh, what's going on? Sorry. I think it's the wrong presentation. Sorry about that. It's this one. That's good. I noticed. On the first slide. Okay, different people. As well as some work we've done together with Jean-Baptiste and Alberto, but I will not speak about any modeling aspect, just the visualization part of the work we've done together. Okay. So that first slide is just to set the context, because we've been seeing a lot of things around at the fire level, on the ground for fire behavior, etc. But here I'm really focusing on the plume and the cloud. I'm not looking directly at the fire behavior or anything like that. And the processes that we are interested in to capture with the radar are all those things here. So the wind change on the fire front, also where potentially the fire front is, and how fast it's progressing, but I won't touch that too much. The firebrand transport, so identifying in the plume if there are firebrands or if there are things that can be uplifted. And then the clouds about the fire, including when they grow, if there is downdraft or if there is something as extreme as the plume collapse. But I won't go too much into this as well. So just here, I will also touch a little bit about the satellite work that we've been doing. But just for the remote sensing aspect of things, this dates from about 5 or 6 years, so there are probably new things in there that are especially for the small sat or the CubeSat. But effectively, the thing we are working with is weather radar. It's usually based on the ground. There is two main possibilities. One is the operational network, so every country will have, or not every country, but most countries in Europe, in the US, and in Australia will have a network of weather radars that covers most of the country. And then we potentially have portable weather radar that are operated by mostly research institutions such as universities, and LiDAR. The LiDAR operating in the near visible spectrum, when the radar is operating in the microwave, so they have limitations one and the other, and advantages one and the other. To my knowledge, people who are operating LiDAR and radar on fires are really a group of few. The people in the US, Craig Clements and Neil Larrow, who are doing this work, and there are us in Australia, but it would be great at some point to see something happening in Europe as well. Because the audience, I think, here is not specifically familiar with radar, I will just speak a little bit about the radar, the concept, and how things works with fire. The very first paper that mentioned an observation of a fire with radar is actually really old. It's from 1950 for a fire that happened in 1949. And if we look at the timeline of scientific papers using radars to look at fire, you can see that it's quite scattered. The papers that were around those times, there are half of them who were industrial fires, so not necessarily bushfires, but there was a fire in a city, and people who were doing weather or radar, weather with radar, they saw something on the radar and they look at it and they try to understand the scattering mechanism. The different colors, they show the different wavelength of radars that can be used. The S-band and the C-band is what consists most of the network. In France, it's mostly C-band with some S-band in the south of France. In Australia, we have also a mix of the two. And then the smaller radars, the X-band, K-band, and W-band, they're mostly research radars, which have advantages and disadvantages as well. And so really recently there has been a growing interest in using radars on fire, but mostly from the groups in the US and us in Australia. And I will show some of that in the next couple of slides. But one of the questions we're trying to ask in our project is also how weather radar can make it to being something used operationally in fire services. And there is a lot of work to be done for this to happen. So I try to separate that into different pieces of a puzzle. One of the first pieces is really theoretical, to understand what we are seeing with the radar and how the scattering mechanism happens. And this is also linked to the microphysics in the clouds and in the plume. Then one of the main objectives is to capture data. And to have good data, we have to go to the fire, and we have to go to big fires, and that involves complex processes, because it's a dangerous environment, of course, and we are going on the ground, so it's possibly risky. So capturing data is important. Another part is to build automatic processing chains, so that when we use especially operational weather radar data, we don't want to be, we want to have a system that is directly producing products that can be used for within the agencies. And then there is a whole aspect about the visualization of the data that can be used for training purposes when we have case studies, and also to integrate that with other observations, such as the satellite. And then the thing which might be the most complicated thing to do is to create a new operation within the fire agency to operate a radar, if they have to operate a radar within the fire agency. And because that's something that doesn't exist, so they will need new personnel, new processes, new everything. What we have been doing is using that kind of setup. So when there is a fire typically progressing in that direction, we scan ahead of the, upwind from the fire, and we are trying, sometimes we scan from this direction if we think that the risk is quite small, and for prescribed burn we could even scan downwind. But we try to be 5 kilometers away from the fire front, and we have this type of radar. There is another radar that is at another university in Australia, which is a bit bigger than that and has a different constraint. It's a bit harder to install, but this one can be deployed really quickly. And when we are there, we do time lapses, we release radio soundings, and we set up weather stations sometimes. This is a video from an helicopter during the Mount Bolton fire in Victoria. It's a fire we went to with the radar, where we captured a really good data set that we've been working on with Alberto and Jean-Baptiste in terms of using that for evaluating the simulations. You can see that for that specific fire, you had hotspots, which are really clear because the fire was burning in a very dense forest on a hill, and the spotting mechanism was landing in a grassland which was very, very dry. And so the hotspots are really easy to spot, to see, as you can see here. And this fire was, the event lasted not a very long time. I think it's just a couple of hours when it was really intense. So here's the data we collected for that fire. We were doing here RHI, which is just a section of the plume, just within the main axis of the plume. The resolution is 50 meters, so you can see that with that resolution we can resolve the pulses. In the Doppler we can see rotation and vorticity. What else do we have here? No, I will show that afterwards. This is an example of some data we collected 2 years ago or last year. There was a fire here, and the radar was here. And for that fire, what was interesting is not really the plume, because the fire was not behaving too extreme, but we saw a line of thunderstorm passing over the fire ground, and we could see the lightning starting new fires at that time. But you see the type of resolution we have with the radar over such an event, and we can see here is just the reflectivity, but we can also get the wind in 3 dimension, which is very useful for forecasting possibly the effect on the fire on the ground. This is another one, which was just at the border between Queensland and New South Wales. For this one, what was interesting, you can see the plume. I will show you after the segmentation I've done where I separate everything. But here it's not separated yet. So you have the clutter. So the thing that stays the same here in the middle is just the ground. And you can see here the plume, which is this bit here. And the thing which is moving through is cumulus. One of those cumulus at least had lightning. So was not all the way to a CB, but probably a cumulus congestus, so creating lightning at 8 kilometer or 9 kilometer, I don't remember. And the interesting bit here is that when this arrived with those clouds, the fire intensity really dropped dramatically. And here is a cross section of the same thing. You can see the plume here. The different variables, this is the reflectivity, the correlation coefficient, the differential reflectivity. So those two, they indicate what type of scatterer or echoes we get in the atmosphere. The very blue color here is rainfall. The very orange here color is the smoke. Here it's close to 1 because the shape is very spherical, and when it starts to be non-spherical and with an axis ratio that is quite different, such a firebrand will be very long in one direction, very flat. It starts to have values that are much lower. So on average here, that's what you get for smoke. And when the rain is falling, you can see as well that the shape of the droplet is in here. That's very spherical, and then here you can see an increase in ZDR when the rain droplets, they flatten as they fall. And so here we could see clearly the rain just arriving on the fire ground and the effect on the plume. Here is the part about, I wanted to touch a little bit about the theoretical part and the understanding we have, which is limited on the scattering mechanism. Here is an example from a paper from Nail, where he showed that this is a LiDAR observation of a smoke column, and you can see at that altitude that there is an extension of the signal, and this corresponds to when you have condensation in the plume, and you clearly see it really, really well in the LiDAR, because in the near visible spectrum there is directly extension of the signal. In the radar, you don't see that at all. You see a continuum. So with the radar, you don't see that condensation elevation. The elevation at which you have condensation in the cloud, or the plume to cloud. And that's an important point, because I think that's one of the issues with radar. You cannot really see that, and you have limitation into how you interpret the signal. But if you combine the two, then you have a pretty good picture of what's happening. So to solve that, we need more observation, but also some scattering modeling. Some people have started to do some of that, but it's very, very limited. And there is only one Institut collection, to my knowledge, of, well, maybe with SILEX you have collected as well some particle size distribution. But the smoke must be really tiny, probably. The collection they got here, they went through a PARO-CB with an aircraft from the NASA, and they collected ash that were, from memory, 3 millimeter, 4 millimeter in size. So I don't know if it's much smaller, isn't it? Yeah. And to my knowledge, that's the only observation in a plume that well, although no, yeah. So in Silex you probably have observation corresponding to the radar echoes for the same voxel. So that would be very interesting to look at. Just here, the way it works, it's really complex in terms of the process, because the electromagnetic properties they depend on the molecular composition, on temperature, moisture, and the mass. Then you have a shape which is usually quite like this, random, but usually ash is flat. And then the way it moves will also have an impact on the type of echoes you have on the radar. So if it's ascending or descending, and then it's the average of the motion of everything within the voxel. And so you have all of those processes that can happen because when the ash starts to fly, it's burning, but when it goes higher, it will get more moist because it will absorb water through the porosity, and then it will have a higher permittivity. And so it will change again in how it will react with the electromagnetic wavelength that's passing through it. Yeah. That's how it looks like in the experiment, the ash that we can see on the radar. But we see ash and firebrands. Not only ash, but it's mainly ash in terms of the number. How much time do I have left? Okay, I will speed up. Thanks. So that's the radar coverage we have in Australia. That's for 75 kilometer, 150 kilometer range. So you can see the coverage that we have is not perfect because there are plenty of gaps everywhere. And usually 75K is what we see as useful for using as for the application of fire. But the main problem is that when we have a radar scene like this one, it's really a mix of plenty of things. As for many operational radar, you have clutter, you have sea clutter, you have insects, and you have smoke. And the main problem is that for all the variables, there is a strong overlap. So you cannot just use one variable or a combination of the variable to segment your image. So we've been working, and that's an example of some of the fire plume in Sydney during the 2020 bushfires. You can see all this thing, but you have a complex scene with a lot of things. So you want to be able to segment that automatically. So the work we've been doing is developing systems to do this. And what we do is that we combine texture using different techniques, but starting with the GLCM, the gray level co-occurrence matrices. So you look at the neighboring pixels and you create a texture based off that. And then you combine that with a clustering method. And doing this, you can then there is an issue with radar, is that it's in polar coordinates, so it's not a grid, perfect grid. And you need to take into account the fact that the voxel is larger as you go away from the radar. If you don't do anything, you end up with this, but we're using a technique where we take into account the effect of the geometry of the radar. And doing this, we can come up with, this is the processing chain. I went really quickly through that, but then you obtain something like this, where you have all your different echoes that are well separated, and you can extract only what you're interested, which is the fire, and in a very automatic way. This is another method that is quicker, that I've developed to be quicker than the GLCM, because it's taking quite a lot of time if it's not on the GPU. This is an example as well for, same as what I showed before, where we do the segmentation and we can extract the smoke from the rest, so the rainfall and the clutter. This is the case I showed before, which we are working on with Alberto and Jean-Baptiste. Alberto submitted a paper just recently on this. But effectively, we are segmenting here as well, identifying what could be pyrometeors within the plume. And we try to link this with spot fires that we can observe at different locations. With the data, we can also get the winds and the wind vectors using optical flow. This is something I've just started recently, but I'm keen to explore this more because this could be very useful for many different applications. This is more of the same other case where we were looking at firebrand transport. You can see in that variable here some core values of ZDR, which are most likely linked to very big scatterer. Same case as before. I will go quickly. This is what you would see from the Melbourne operational weather radar from Laverton. So you see, you'll have that versus what I showed in the previous slide with the much higher resolution. And you see the benefit of having a radar which is closer in terms of what you can see. This is some visualization that I've done following my visit to Corsica, thanks to what I learned with PowerView with Jean-Baptiste. But effectively, that's a fire we went to in Walangara. I didn't show that here, but this is the smoke plume. This is the reflectivity, so how strong the echoes are reflected, and those are the rain cumulus coming through the field, which were segmented with the technique that I showed before. And so once you have that, what is quite nice is that you can, so that's just the time series of the same thing. But and here is just the smoke, but what is quite nice is that once you have the segmentation, you can, for the rainfall, you can also estimate the precipitation over the fire ground as an accumulation, as the clouds are passing by, something like this, with the blue colors. And so this is just some work we've been doing using a combination of radar and satellite, because you can use the radar as a reference to train your satellite to identify pyroconvective clouds, especially pyro-CBs. You can use the strength of the radar, which can tell you how high are the clouds. So this is the radar ecotop height. So that tells you what is the last voxel that sees a certain reflectivity. So you can have the height of the clouds, and you can use that to validate the algorithm you can develop to identify the pyro-CBs. And that's what we've done here. It's just a sequence of steps we do to identify those. And you see here those red areas are pyro-CB during the black summer. And one of the things we've done especially is to remove the misidentification of the anvil, because you have those very big anvils, but you want, sometimes they are detached from the pyro-CB, and you want to remove them in the identification. I think one of the cases here, yeah, no, not here, sorry. Yeah, here, I think there is one case. This one, for instance, initially was labeled as a pyro-CB, and with the new technique, we just removed that misidentification. And that's it. I think I had a slide here from from a presentation I did a long time ago, but that's one of the things we are trying to do now. We have discussion with the Queensland Fire Service about getting some funding to put a radar on a truck, which would eventually look like that in ideal world. And the idea will be to have the data flowing directly to people who can interpret. So something simplified so that it can be easily understandable, that can go to the regional center, but can also be used by researchers to improve the algorithm, etc., etc. Yeah, so that's all. I hope I stick to the time.